All right. Yeah, thanks everyone. Thanks to the organizers for letting me be a part of this. And inspired by Professor Pohl, I guess at some level, I sort of cheekily changed the title of my talk to AMO Theory with the O is for open. I guess this spiritually connects to some stuff that we heard from Anna yesterday as well. And I guess here, open, I kind of mean in two senses. One, in the broad context of the title of the workshop, in terms of where things are going as an open field, but also open in the context of open systems and thinking about noise motivated by these AMO settings. So, although this will be a theory talk, and kind of nicely following Tommaso's talk, I would say that maybe one of the ways to think about where AMO questions can take us is motivated by this pretty remarkable recent slew of advances in terms of modern AMO experiments, where in some sense these AMO experiments are allowing us to ask questions that reach pretty far beyond the regime of traditional quantum many-body physics and equilibrium and kind of stat-mech classes that we're all used to taking. And I would say that, these days there's been beautiful demonstrations of pretty large-scale many-body coherences, GHZ states, spin squeeze states. There's an ability to repair out of equilibrium initial states and look at complex quench dynamics, as we've heard about already from Tommaso. There's the ability to engineer in real time, time-dependent Hamiltonians, and oftentimes these days one also has the ability to microscopically read out in real space correlation functions of a many-particle system. But, of course, with all of these various aspects that are enabled by AMO experiments, one should also realize certainly that at a fundamental level, these systems in the present time are open quantum systems, so they're always coupled to some noise, some environment, and there's a slew of ideas in terms of understanding what that openness does. So I want to give the perspective somewhat that a lot of times the way we think about, or the way we teach our students to think about openness is saying, well, we have an experiment that we think should be pretty much coherent, but we ultimately think that noise is affecting something about the outcome of the experiment. Let's do some simple phenomenological, maybe master equation simulations to understand how that noise impacts the nominally unitary dynamics, and let's see if we can agree with the experiment and learn something about that. I hope to give the perspective that thinking about noise as an openness as a fundamental aspect of these types of experiments motivates possibly a lens into new types of questions. And in particular, I would say that along the route of kind of benchmarking, trying to understand and characterize noise and decoherence, one can ask a sort of classic question in the context of stat-mech, which is, can one legitimately think about there being universality classes for different types of noisy analog simulations? So we're used to thinking about defining quantum dynamics in terms of universality classes, in terms of critical exponents for the dynamics of a closed system. Can we ask whether or not there are similar universal behaviors that one can categorize in the context of noisy quantum simulations? And the second question, which is maybe a little bit more quantum information-y or computer science-y in spirit, is and one that's motivated in the last couple of years by questions about quantum supremacy and quantum advantage, is what truly is the complexity of classically simulating a noisy quantum experiment? And here, I'll split my talk into sort of two parts that are very much guided by the same framework. And the first part of the talk, I'll really ask this question in the sort of simplest and broadest sense related to this understanding universality classes. And the question is, how exactly do we think about characterizing the impact of noise on the fidelity of quantum dynamics, for example, in the context of an analog simulation? And I'll emphasize that part one, unlike part two, is relatively practical, but not at all rigorous. I'll try to give some phenomenological equations I think that can get you very far, but which are not provably rigorous. And I would say that maybe the simplest proxy that one can use for kind of characterizing the fidelity of quantum dynamics might be the classic Loschmidt echo, which all of you are familiar with. The Loschmidt echo, of course, says that, well, let's imagine taking a particular fiducial state, evolving forwards in time, evolving backwards in time, and measuring the fidelity to recover an initial state. So the Loschmidt fidelity often has two phases. Sometimes people talk about the Loschmidt fidelity in terms of a many-body fidelity, sort of an actual many-body overlap. but I'm actually going to take a more single particle perspective and ask about the fidelity of a local or observable. So for example, if you start in some initial state for some qubit that's 0, what is the fidelity of ultimately projecting back to that 0 state? So it will not be sort of a many-body overlap that I'm considering for the Loschmann echo. This is very much spiritually related to NMR experiments where people think about Loschmann echoes and where the observable in that case is the recovery, the magnetization, which is again a sum of local observables. And I will hopefully convince you a little bit that if we think about this proxy, this kind of obvious question, how do we characterize the fidelity of noisy dynamics? And we think about there and back as the proxy for characterizing those dynamics, that understanding the decay of the fidelity of there and back, one should naturally believe that there are universal behaviors depending on dimensionality, structure and range of interactions, integrability, conservation laws, etc., like one would normally think about in the context of unitary circuits or unitary dynamics. The second part of the talk is going to be a different question, and it will be rigorous, but not very practical. So I'll give bounds that are actually rigorous, but they will have little impact in the sense that the bounds have very, very large polynomials. And the question I'm asking is, how does noise impact the complexity of quantum dynamics and the complexity of classically simulating quantum dynamics? And here, even before I begin anything about the talk, I think there are two very simple limits that you all know extremely well. On one limit, you know that with a little bit of structure, a lot of structure, and maybe a lot of overhead, one can do error correction. So that means that one can encode in the physical dynamics of a system, maybe with some environment as well. One can encode fault-tolerant quantum computations and do fault-tolerant quantum circuits, and we believe that those should be classically hard to simulate. On the other hand, specifically, again, motivated by some of the questions and really beautiful results coming from the Google team, there were questions about, how difficult is it to simulate noisy random circuits in terms of either sampling from the output distribution of those or computing expectation values of observables. And it turns out that, unsurprisingly, already maybe a decade ago or so, there were results that say that, if you have a sufficiently large noise rate, it doesn't matter what circuit you have, a sufficiently large noise rate always means that you can simulate something easily. And the idea is that if you know that within sort of log depth of evolution, you already basically get to the fully mixed state, then that's the answer. You don't need to ask about how difficult it is at all. But the question here more recently has been, what if you just have a little bit of noise? Your experiment is pretty coherent, but is it still sort of, easy, or is it difficult now from a classical simulation perspective? How complex is the classical simulation? And specifically in the context of random circuits, there's been remarkable results from Dorit and company, where they essentially proved that for any epsilon amount of noise, there is a classically efficient polynomial time algorithm for sampling out of a noisy random circuit. This makes use crucially of the fact that the circuit is random. So you can kind of ultimately, when you average over circuits, map things to classical Markov processes, and you do a lot of analysis in that context. Was there a question?
Does that result allow measurement and feedback, or no?
No. Good. So, so the question is, of course, where exactly is the sharp divide between these two regimes that we sort of know? Is it that we should expect most things that are not random circuits with a little bit of noise are really, really hard to simulate? Or that most things with a little bit of noise that are not random circuits are actually pretty easy to simulate, and the things that are hard to have polynomial time classical algorithms are really only things that are very close to fault-tolerant computations? And it turns out that I will give an algorithm that provides a polynomial time classical algorithm for both sampling from and computing expectation values of generic noisy random circuits, which pushes this quite close, I would say, to the fault-tolerant side of things. Maybe not so surprising, but nonetheless interesting. So the framework for answering both of these questions I will use is that of operator sizes. And in particular, it's a framework that actually a lot of people in the community have been using, but I'll try to introduce it in a very simple way. So the idea that we're asking about in terms of answering these questions is, what exactly does the dynamics of quantum information look like in a noisy quantum simulation or a noisy analog device? And I would say that one way to characterize the dynamics of local quantum information is in the Heisenberg picture that you all know well, where you say, well, if I have a local operator at time t equals 0, how does it evolve under unitary dynamics? Well, there's a light cone. It'll grow into a complex operator that is a superposition of many different Pauli strings, for example. And the operator will generally increase in size, and it will do so at a bound set by the light cone associated with the unitary, which may be different depending on the range of the interaction. So this framework for thinking about information dynamics people oftentimes call the scrambling of quantum information, or looking at the operator growth, sort of the Heisenberg picture compared to the usual state-based evolution. One metric, maybe the simplest metric to characterize the way operator sizes change, is by looking at operator size distributions. And again, this is an idea that kind of has been winding its way through the community in many different ways, both numerically and sort of analytically. And the way I define sort of the specific size of an operator is I say, okay, I'm going to look always at Pauli strings, and I'm going to define the size of a Pauli string in particular as the number of non-identity elements. So for example, for this specific Pauli string P, the number of non-identity elements is 6, and we would say that this Pauli string has size 6. And what that means is that any time-evolved operator always has a size distribution. It can be characterized, the dynamics of information can be characterized by the dynamics of operator size distributions. And I'll try to convince you, introducing a new way to characterize something, one should win something from this, and I'll try to emphasize to you phenomenologically where we win. So I would say, we imagine having an operator that may be local at time t equals 0. At later times under unitary dynamics, you expect to be able to decompose this operator into a sum of many, many different Pauli strings, up to 4 to the n at some point. And we can say that for each of those Pauli strings, we can characterize the size, exactly as I say here, and then we can make a histogram and say, what is the probability distribution or the size distribution of the operator at time t in terms of the sizes of the Pauli strings that make up that operator? And of course, this size distribution will have a mean that I call S bar, have a variance that I call delta S, both of which will become important. And basically, the intuition should be at a very basic level that as a function of time evolution, this size distribution moves to the right and gets bigger. It turns out there's been quite a lot of work on this already, and in the context of purely unitary dynamics, there is a very reasonable perspective that these size distributions evolve in a pretty universal manner, and the universality class of these evolution of these size distributions depends on the things that you would naturally expect universal dynamics to depend on: the dimension of the system, integrability, conservation laws, range of interactions, etc.
Question.
Yeah, please.
So is that true for the typical case, which is usually how random, or is it also true for the useful type of?
Useful. It's true for basically everything. So local interacting, one-dimensional, one is too easy almost, locally interacting 2D Hamiltonians that would generically exist, dipole-dipole interactions, all of this, this operator size distributions typically have a pretty similar dynamics. So, but I'm hoping to ask the question in terms of using this lens of operator size distributions, but I'm hoping to ask a question about classifying or thinking about noisy quantum dynamics and not just unitary dynamics. So let's ask ourselves a little bit from this kind of a perspective, and with the specific proxy of asking the question about the fidelity of a quantum dynamical system via the Low-Schmidt echo, let's see how to build these two together. So I would say that if you think about an operator size distribution lens or perspective on a noisy Low-Schmidt echo, you'd say, well, I'm interested in measuring, let's say, the projector onto 0. So how likely is it for my state to come back to the original state? Then you might say, well, from this perspective of operator growth, if I think about sort of, where noise kicked my system, the places where noise kicked my system, as long as the final measurement lives in the light cone of that, those are the noise events that will affect my final result. If I have a noise kick somewhere over here, very close to the end of the circuit and very far away, there's no time for the unitary dynamics to actually lead to some effect on the ultimate measurement. The exact opposite perspective is to say, well, we can imagine sort of looking at the backwards light code and just thinking, in terms of what is the set of operators or the set of things within this light cone that can affect this measurement. It's just literally turning that triangle in the opposite direction. And again, any red dots that correspond to noise kicks that live within this purple region, or the influence region of the noise, will ultimately be able to affect the measurement outcome or the fidelity of my Low-Schmidt echo. And of course, we realize that at intermediate times here, of course, at intermediate times here, the operator may be a sum, should be a sum of many, many different Pauli strings. But from a noise perspective, as is again natural, you'd imagine that those highly non-local operators that make up what the operator looks like at intermediate times should be more sensitive noise, simply if you assume that noise acts individually on each qubit in the system. All non-surprising. It turns out, under some pretty reasonable assumptions, like Susanna was saying, sort of generally ergodic many-bit dynamics, as long as you don't choose the dynamics to be too bespoke, it turns out that for large Pauli strings, noise decays the amplitude of the Pauli string that makes up this operator at a rate proportional to the size. And that's almost obvious trivially by just looking at the picture, because there are more places for noise to act on a large size Pauli string. You expect that the rate at the noise decays, the amplitude of this coefficient is going to go as gamma, some rate multiplied by the size of that Pauli string. So with this extremely simple idea, it turns out one can already get kind of a reasonably rich interplay between the growth of the operator dynamics from unitary physics and noise, and we can understand how that already phenomenologically can impact the Loschmann echo. Okay? So I claim that we should think about the operator size distribution, and the unitary dynamics for operator size distribution will generally push the mean because the operator is growing to larger sizes. It may, depending on the nature of the interactions, also grow the width of that operator distribution. And the impact of noise is that it should damp stuff, but it should damp stuff more quickly for large size operators than it should for small size operators. And what that means is that there's kind of naturally two effects. Overall, the area under this curve is going to decrease as a function of time, and it'd be nice to write a phenomenological equation for the way that decreases. And second, the overall, instead of moving to the right, the noise should generally shift things to the left because large size operators should have an amplitude that decay more. And it'd be nice to be able to write down a phenomenological equation very simply that characterizes that shift to the left. Katie?
Okay, so actually I have two questions because I have a new one after you. I guess you need to renormalize this probability distribution after you do this shift?
Nope. So actually the change in this probability distribution is exactly the value of the Loschmann echo. So it turns out, exactly. So the way to think about this is actually, so you have an operator, and basically, the operator is going at initial local operator. At later times, you can expand this in terms of Pauli strings, and the sum of all those coefficients will sum to 1, basically. There's a normalized distribution. And if it's 1, that means in principle that all of the quantum information about your original operator is in that distribution. It may be that it's spread out now in very non-local operators of the distribution, but it's all there. When you change the area under the curve of this distribution, the Loschmann echo, you are changing the amount of information that the system retains about that initial operator. Second question? You said there were 2.
Yeah, I think you may have answered the second one. So,
Oh, that's strong.
I'll ask it at the end.
Sounds good. Okay. And so that's what I'm trying to say. So the picture I want to think about here is that, there is, it's complicated. You have lots of different microscopic Hamiltonians, lots of different ways noise can act. You have T1, T2, et cetera. But thinking about things in terms of this distribution of operator sizes, I want to write down phenomenological equations that can make predictions about experiments in an interesting way that just think about the way, Pauli strings the size of operators should change under decay. So the first effect that I mentioned is in terms of the decrease of the normalization, exactly as Caden said. You can imagine that the decrease of normalization, just literally coming from a one-line calculation, is that time dynamics of this will decay in terms of some rate gamma multiplied by the average size, and that's the way the normalization will change in time. And it turns out this normalization, again, is exactly the Loschmann echo, and encodes how much information about my initial operator remains in the system. And the second thing is a shift in the shape. But the shift in the shape, of course, kind of cares about the width. Because the only reason, if you have a delta function, then all that's doing is decreasing in time. The change in the shape comes from the fact that large size operators should decay, the amplitude of the coefficient of large size Pauli strings should decay faster than the amplitude of small size Pauli strings, and this squeezes things, so clearly you care about a variance. So the change in the mean will care about the unitary, which is shifting to the right, but it'll also decay at some rate gamma and the variance of the system delta S should naturally enter. So two phenomenological equations, one can't prove any of it, but I claim that maybe this is the right way to think about noisy analog simulations or noisy dynamics in general. So I claim, we can read the paper in a little bit more detail, I won't go into quite all of it, that there are, in fact, multiple different reasonable universal classes of noisy quantum information dynamics that depend on dimensionality, range of interactions. Is it integrable? What are the conservation laws? How non-local are the interactions? And in particular, I'll give a little bit of an example that focuses on the non-local case, something that you've all heard about. Non-local interactions are relevant in cavity-mediated interactions for spin squeezing, in simulations of the SYK model, and in particular, here in the next slide, I'm going to motivate this kind of from a small-scale experimental situation related to NMR, which is indeed one place where the low-Schmidt echo appears often. I apologize that, despite this is an AMO talk, it has been an AMO type experiment that does the same type of low-Schmidt echo that many of us think about, but it'll be a specific experiment in NMR on about 1,000 spins, and it is. I think of it as being very much all-to-all because the unit cell contains, of this adamantane molecule, contains I think 12 nuclear spins, and there are essentially 16 neighbors. So it's 12 nuclear spins interacting with 192 guys, and that basically means that even though there's 1,000 spins, it's not really a very, very large scale system. It's actually quite strongly all-to-all coupled in some sense. So the experiment measured the low-Schmidt echo, which I'm characterizing, which I'm writing down as the number n over here. And what it did was it did forwards and backwards evolution, and it made the backwards evolution imperfect to simulate the effect of some noise in the system. And it did so by just saying that, okay, I forwards evolve with you, and now instead of backwards evolving with the same dipole-dipole interaction, I'm going to backwards evolve with a dipole-dipole interaction plus some perturbation, in their case, some field. And the strength of that perturbation is given by P. And the thing that they saw that they emphasized was kind of weird was in fact that the decay of the low-Schmidt echo clearly depends on how different forwards and backwards evolution is. If it's not any difference, then it's just going to be 1. But they find that the rate of the decay is actually not the best plot to show that, but it's the best plot to show this. They find that varying P, the rate, which is the slope of the low-Schmidt echo decay as a function of time, the rate of the decay of the low-Schmidt echo was always 13.5, independent of the amount of noise that you apply. So that was kind of interesting. And they say, well, we know that the low-Schmidt echo is only decaying because of noise, and noise clearly has an effect, but the amplitude, the size of the noise, does not impact the rate at which the low-Schmidt echo decays at all. There's some weird universality, something happening over here that we can't understand very easily. And they had a proxy for measuring the size, kind of using OTOX, out-of-time ordered correlation, which is not super important, but the proxy in the experiment for measuring the size distribution, the mean size distribution in the NMR experiment of an initial local operator as a function of time. And they find that when the noise is very, very small, it's kind of what you would expect for all-to-all because it's exponential. And then for large amounts of noise, or in principle, imperfect backwards there and back, you find that it saturates some value. And again, this is maybe also a little surprising. You expect, well, if you're an all-to-all system, you do really expect that the operator size distribution, the mean, is getting larger. But it's saying here that even for, in principle, single particle noise, T1 or T2 on a per qubit level, it will ultimately lead to a saturation of the average size of the noise, average size of the operator distribution. And it turns out, just using the two phenomenological equations that we said, just very intuitively, by thinking about the operator size distribution, we can understand all of this. And the answer is that if you couple those two differential equations, and you can literally solve them by hand, you don't even need a computer for this, you can show that the size, the mean operator size as a function of time will plateau to a value that's 1 over the noise rate. Okay? So it is exponential. It goes as e to the lambda t. It's exponential, and actually the plateau is sort of, it goes to a plateau that's lambda, the Lyapunov exponent divided by the noise rate. So you can see, I apologize for using different letters. Epsilon and gamma here are the same thing. So for epsilon goes to 0, it's just exponential. But as you increase the noise rate, you find different values of plateau, like even here. But crucially, remember that phenomenological equation we expect over here. If at sufficiently late times, S bar plateaus to a value that's consistent with 1 over gamma, But dNdt cares about gamma multiplied by S bar. This immediately tells you that indeed the Low-Schmidt echo decay rate, although it's caused by imperfect there and back, should be independent of the noise rate for any noise rate. Again, from the simulations, this exactly matches that although the decay happens at a time scale where the plateau happens over here, the rate at which it happens is independent of P, in agreement with what the people in NMR were seeing when looking at the Low-Schmidt echo. And this is just trying to convince you that, in principle, thinking about noisy quantum dynamics, one can maybe get very far by looking at phenomenological equations, thinking about things like, could be the size distribution, could be other things, in terms of understanding universal physics in the way these dynamics happen. Good. So let me now move to part 2 very quickly. Yeah, Kate, please.
So sort of related to that comment, so it's clear a lot of interesting and important stuff is happening in these distributions, but underlying your motivation in things was that this should tell us something about the simulability of the systems, right?
Yeah.
And it seems like there's quite a bit of missing information there in the size distribution, because I could do, for one size, there are exponentially poly strings, but maybe only some exponentially small fraction are actually there. And so in something like an SPT, you'd have like a very long string. So do you have any thoughts, like, are there ways of capturing that going beyond the size distribution, or does it generically not matter? What's the...
Let me see. I'm not sure I can perfectly parse the question, but let me parse it in the way I want, and then let me see if I can answer it. So I think I think part of it will answer part 2. So the first thing I should say is that at least for the SPT, it can be very non-local, but actually it's not clear to me necessarily that this is just a very aside comment, that the non-locality doesn't necessarily matter exactly. It's sort of the size, the number of non-identity elements. So locality in terms of like a strictly local sense actually is not exactly the thing that matters for operator size distributions, but you are right. You can ask a question, maybe there's 2 perspectives. I would say, in the size distribution, there can be many different breakdowns of operators that give you the same size distribution. And that means that if you want to think about simulating the exact dynamics, it's not clear that the size distribution tells you everything. On the other hand, I would say that especially my perspective is maybe the opposite, that if you really want to simulate the size distribution, you have to care about, all, in principle, 4 to the n Pauli strings and what they look like. So that is going to be exponentially hard just from a counting argument. But I will give you part 2. Let's see. So part 2. But in part 2, I'll answer the question and just say that there is actually a polytime algorithm for simulating essentially generic noisy circuits, period.
Yeah, so we can discuss more offline, but I guess my concern is more that for things that look bad from this bound, they still might be classically simulable.
Things that look bad from
things
this
that look
bound?
hard to simulate from this stuff. Let's just talk more. Keep.
I'm not sure. Okay, well, I think the bright line you'll see is very far shifted in the sense that I think the things that are eliminated and that I know should be hard are things that you almost certainly can't, because I can basically encode using those things arbitrary quantum computations. At least that's what I think. So let me be specific about what the setting is for part 2. I wanted to consider a noisy quantum circuit. So this could be noise on top of analog quantum dynamics or noise on top of a digital quantum circuit. And I claim that we can provide for any observable O that you would like to compute the expectation value of, we can provide an efficient classical algorithm to compute, indeed, the expectation value O for a state evolved under the quantum channel associated with the circuit plus the noise, with a small average error over input states drawn from any complete basis. Okay? So I'll unpack this last statement a little bit right now. So again, it's with a small, imagine sort of, drawing, asking yourself, what exactly is the expectation value? Usually you're asking about it with respect to some ensemble. And I'd say, as long as you draw it over some reasonable ensemble, computational basis states, any other reasonable ensemble, I can guarantee you an efficient classical algorithm that has a small average error over such input states. Okay? First, what exactly do I mean by efficient? Well, I mean it runs in either polynomial or quasi-polynomial time in n, the number of qubits, d, the depth of the circuit, and an epsilon, the tolerance, the error tolerance that you set for the problem. Whether it's polynomial or quasi-polynomial depends in the kind of quantum information literature on whether you're using a noise model that's called the uniform noise model or you're using the gate-based noise model, and I'll unpack that as well. the restriction, oftentimes for people who haven't thought about this a little bit, the restriction to ensembles of input states seems weak. It says, well, why can't you do this for any arbitrary input state? Isn't that a lot weaker? Why do I have to restrict to an ensemble and an average of that? You have to. The only possible result always has to restrict to an ensemble, because for any fixed input state, I could immediately, in principle, for a fixed input state, design a bespoke, noisy quantum circuit that actually implicitly is doing error correction on a particular input state, and that would immediately allow me not to be able to simulate that, at least from the right-hand side of my initial thing. So you can only ever make statements at an ensemble level. Okay? So this is the strongest type of statement that you can make. Yes?
Just a quick question. In the first part, you were talking about random circuits, correct? There was some sort of randomness?
No, yes, that's right. So when I was talking about part 2, exactly, perfect. So
just understand the
exactly. So comparisons. So in part 1, I was talking about the Loschmann echo. So that was just about it was not about random circuits necessarily. It was in fact about generic types of dynamics with different Hamiltonians. Okay. Here in this particular case, where I was talking about random circuits, was in terms of where there are extant results in the literature. So that was sort of specifically kind of the motivation for part 2, which I'll kind of get to here. Good question though. So again, just following Tommaso's questions, let me very, very clearly state where sort of our result falls. So previously, before us, there were works that showed that specifically, indeed, for random circuits, either computing expectation values or sampling, and the sort of supremacy Google approach, that there are, for arbitrarily small amounts of noise, polynomial time algorithms to do both of these things. And there were also, specifically in other bespoke setting called IQP circuits, instantaneous quantum polynomial circuits, there was also results showing that you have polytime algorithms for expectation values and sampling. On the other hand, for any circuit, so this is not circumstance structure, for any circuit, if you assume that you can put any input, as I just said in the last slide, and either in the uniform noise, I'll explain that, or the gate-based noise, here you can have hardness results knowing that cannot be polynomial time, must be exponential time, hardness results using quantum error correction results. What our result does is it basically extends this almost all the way to the any circuit, any input case. We show that for any circuit and almost any input, averaging over ensembles of inputs from a computational basis, that one, again, has either polynomial or quasi-polynomial algorithms for classically simulating expectation values or sampling, depending on whether you have uniform or gate-based noise. Actually, since I'm already talking about it, I'll just mention here, uniform noise model, that means that in quantum computation, the uniform noise model is that noise is always acting on your qubit no matter whether you're touching it or not. So you have idle errors. In the gate-based noise model, you only have errors in the qubits when you do something to the qubit. And these are the two different noise models. And the distinction seems pedantic, but it's quite important.
Just to understand exactly the edge case that your point is that there are circuits for which you could design a particular initial state that performs quantum.
Perfect.
But
perfect.
kind of like most circuits that you actually want to do don't actually have that. So your belief effectively is that for generic circuits, any input state.
Exactly. No, that's not. You still have to average, even for generic circuits. I mean, yes, that's right. Yeah, for generic circuits, basically any. Yeah, that's right. That's exactly right. That's correct. But there is the edge case that you have to be careful.
What is quasi-polynomial?
It means there's a log, so it's log instead of constant. So it's like exactly. So you have a log power to the log n. Good. So let me again take this sort of operator-sized lens or this operator-sized distribution lens on relating noise to complexity of classical simulation. It's kind of obvious what you do. You take a quantum circuit and you try to decompose the evolution of operators into Pauli string basis, into the Pauli string basis at each time step. And already in the last couple of years, there's been a lot of intuition built up in the community that there is a very, very natural connection between the paths of Pauli strings that are hard to simulate and those that are strongly damped by noise, those that have large size. And it turns out that indeed, one very simple intuition to see this is that if you care about, Pauli strings of size L, there are only a polynomial number of such Pauli strings that you need to keep track of, as opposed to an exponential number of high weight configurations that you would in principle have to keep track of if you wanted to get the dynamics exactly. So what's the obvious strategy? Well, we'd like to somehow approximate Heisenberg time evolution via only low weight Pauli operators or small size. Weight here is equivalent to size that I defined earlier. And it turns out there are actually two different algorithms, clearly because the noise models are quite different from each other. And the two different algorithms are going to work for looking at the classical complexity of simulating circuits in a uniform noise case or a gate-based noise case that I've already explained. And I'm just going to try to give you a little bit of a sense of the strategy for one of them, because ultimately it's sort of, there is a rigorous algorithm, so it's kind of cute to give you a little feeling for sort of where the essence of the proof is. So it turns out that in the uniform noise case, what we do is instead of just looking at the size of Pauli operators and truncating based on that, we actually look at Pauli paths. So as a local operator evolves in time, as we said, at late times or intermediate times, it'll be a sum of many, many different Pauli strings. And we just take one of them, and we say, okay, that's one possible path that it takes. So people talk about this as sort of the Feynman path picture of how an operator evolves, and that's sort of the Pauli path picture for this type of circuit dynamics. And in principle, we're here going to employ a strategy where we try to approximate the evolution, keeping Pauli path with a space-time size, so in both space and time, all non-identity elements are counted. It's not just in size at a particular point in time, less than some size L over here. And what you want to prove is that when you do this truncation, you don't mess things up too much. And the way to do that carefully, it's really a combinatorics question. Taking all of these Pauli paths, what you essentially do, the essence of the proof, is trying to group the paths in ways in a tree-like structure so that you make the minimal number of cuts so that you can prove that you don't mess up the expectation value in sort of the smallest way. And there's very nice groupings that you can do such that you minimize the number of cuts. And by doing this, it turns out that we end up with a polynomial time algorithm, which is polynomial, as you can see, it doesn't depend on depth, polynomial in the number of qubits, and also polynomial in the error tolerance that you want to state epsilon. You should note, when I said rigorous but not practical, that it's polynomial in the error to 1 over gamma. So if gamma is a very, very small noise rate, this can be a very, very large polynomial, but it's a polynomial nonetheless. It turns out that when we go to the gate-based model, actually, it's easier to do things, we can only kind of do things with truncating Pauli operators. The reason why you get to do paths over here, the paths ultimately means that you clearly get to better bounds, because you're bounding paths which have lots both in time and space. But it turns out that it's much, much harder to make sharp statements about the error that you're accumulating. But the key about uniform noise is that uniform noise is so strong, you have idle errors everywhere, that you never have to go beyond log depth, essentially. So you can live with the fact that the error bounds are not that good and still get overall an algorithm that is better, polynomial versus quasi-polynomial, from the gate-based noise model. Okay, just 2 more minutes. So let me give kind of an implication. So there are some interesting, I think, rigorous implications that, again, may not be practical, but I think are quite important to state, which is that there's a very immediate implication from the existence of our approach for quantum error mitigation. So, I mean, I'm sure many of you are super familiar, maybe even more than me, but the aim of error mitigation, there's lots of really nice papers from IBM looking into this, is that one hopes to recover the properties of some ideal circuit by looking at the scaling behavior, oftentimes, of a noisy circuit. So the classic example is zero noise extrapolation. You do a circuit with successively more and more noise, and you extrapolate the answer for an expectation value down to the zero noise limit, and you say, okay, that's one strategy for error mitigation by using noise to extrapolate to the ideal answer. And such error mitigation is known to require exponential sampling overhead. So for a circuit size with n qubits, you may have to run the experiment exponential at n times to do this type of an extrapolation for certain circuits in the absolute worst case, but it's not known whether this overhead, I mean, clearly it doesn't extend to every single circuit, and the question is, how generic is that exponential overhead? It turns out the answer is quite generic. And the answer is that if you do not believe that your noise rate improves with qubit number, it's very important. So, the statement is that if you believe that, as you increase, let's say at a point in time now in humanity, you have, system size increase the number of qubits, but the noise rate doesn't change, then it turns out that any quantum circuit for which error mitigation is efficient, which means you do not have an exponential sampling overhead for the error mitigation strategy, must be classically simulable. If you believe that as you increase the number of circuits, which I think is very reasonable, this is what Google says, as we increase the number of qubits that we have in our system, we do expect the noise to get better as well. If it gets better as 1 over n, then this doesn't apply anymore. But absent the noise rate improving as a function of the number of qubits, any quantum circuit for which error mitigation works and is efficient must also be efficiently classically simulable. What that immediately tells you is that, in some sense, there's a super simple litmus test for, is my experiment hard to simulate classically? And the answer is, how much does the outcome of my experiment depend on noise? If it depends a lot on noise, then indeed if it doesn't depend very much on noise, which means that error mitigation kind of works well, then it actually must be classically simulable. And only those quantum circuits that are highly sensitive to noise, they must fail at some rate that goes as 1 over n, are ones that cannot be classically simulated. And I'm not saying that it's easy, one can still claim advantage in real time, but from an exponential scaling perspective, it's classically efficiently simulable. But of course, on the flip side of this, it's kind of really cool. There are lots of new numerical strategies, density matrix truncation, dissipation-assisted operator evolution, DOE, that utilize this idea exactly to be able to try to simulate complex quantum dynamics by only keeping track of kind of low-weight-ish stuff. All right, so with that, let me, I'm almost perfectly on time. Let me thank you for your attention and really, again, say, this work was, spearheaded, on all levels, really, by a former student of mine, Tommy Schuster, and sort of all credit goes to him. He's now a postdoc at Caltech, and the latter piece of the work was in collaboration with Xun Gao and his student Chao Yin. Thanks very much.
So there is, since a couple of years, this concept of like pseudo-entanglement, pseudo-magic, etc., which basically says that in general, most entangled and most magic states are efficiently numerically calculable, which means polynomially to come exponentially close to the true one. So there must be some kind of connection between that.
Yeah, okay, so that's actually just weird. Actually, I think maybe the connection is indeed actually, even before, this is a rigorous result, so I mean, actually, quite a lot of people were pretty excited.
And these things are also rigorous, I should say.
Right, okay,
Yeah.
okay, sure. I mean, I don't know enough about them, but I'll say maybe in the spirit of the question, if I can try to connect it a little bit, I think with what I understand, actually, there was a very large amount of expectation this was the case. There were like numerical simulations, in 1D matrix product or matrix product operator versions. There was, I think, a reasonable amount of expectation, maybe from rigorous examples in the context of these specific entangled states, and more generally from numerical examples of kind of more generic things, that there probably should be a polytime algorithm for noisy, generic simulations. But indeed, sort of, actually figuring out the algorithm that does that is a little bit more complicated, and that's kind of, it is a sort of specific contribution in that way.
Okay.
Yeah.
This is more of a curiosity, but you mentioned that the distribution of S essentially becomes sharper and sharper as time progresses, right? Is there any interesting physics to the large deviations, essentially to rare events? Is it, for example, is it heavy-tailed, the distribution, or is it, Gaussian-like?
Yeah, actually, I think in some sense, the case without noise, one can ask more questions about that, actually. So there is, thinking about moments of that distribution is one way that people think about classifying distinctions, subtle distinctions, in the unitary dynamics case. I think the tail, at some level, the heaviness of the tail is kind of cut off very, very quickly when you have noise, because you have a damping rate that's proportional to size. But indeed, I think this idea of looking at moments of that is powerful when you think about classifying unitary dynamics.
So a very naive question, does this actually kind of have any implications for the usefulness of quantum computers, in the sense of saying, if I'm always going to be able to simulate them classically, I don't really need them?
Yeah, so it's beaten into me that I have to be careful about what I say here. So I think that the answer probably, and I do believe this, is no, not really, in the sense that here it is really rigorous but not so practical. So even from the perspective of error mitigation, you can still win a ton actually, just practically by doing error mitigation, like orders of magnitude. But there is a strict sense in terms of scaling that, indeed, if ultimately you have an efficient error mitigation strategy, then it must also be efficiently classic simulable. But the order one factors can be huge, and those order one factors, I think, really are very relevant in both the near term and probably the future as well.
All right, I think maybe we should wrap up there since you're eager. Oh, do we have a cutoff pretty soon here? Yeah, so let's wrap up by thanking Norm and all of the speakers again, and everyone.